Well, what's up, everybody? Congratulations if you made it to question number 6 and you've just been going 1 through 6. I'm impressed that you stuck around this long. If this is the first one of 2024 that you're looking at, also props to you because we're going to learn some calculus either way, right? But this is the final question on the 2024 FRQ for Calc AB. It's an interesting looking question. We got these two curves. I'm going to have the curve over on the left side of this YouTube video. I won't have it on this sheet, so I may just try and ask you guys to imagine that I'm putting certain things where, but we'll work on it the best we can. But let's take a look at this question together. So number 6, it says the functions f and g are defined by, I'll kind of put this up here, f of x is equal to x squared plus 2, and g of x is equal to x squared minus 2x, as shown in the graph. So they are clearly pictured in the graph, pretty easy to track with. So yeah, part A says, let R be the region bounded by the graphs of f and g from 0 to 2. So we're looking on the interval from 0 to 2, as shown in the graph. Write but do not evaluate an integral expression that gives the area of region R. Okay, so this integral, we know that for area under a curve, we're going to integrate over my bounds, which in this case are from 0 to 2, right? Region R, it's bounded from 0 to 2. And then on the inside of this integral, I'm going to take the top function and then subtract the bottom function. They're labeled really clearly, but f of x is on top and g of x is on the bottom. So I will do f of x minus g of x. I guess I could put an extra set of parentheses and put my dx. And this will represent the area of region R. And one short little note, the reason that we do the top function minus the bottom function is because we're integrating essentially the distance between those two functions. Like those little rectangles that we're creating when we think about integration, the height of that rectangle is the difference between f of g, or f of x, and g of x. And we want that difference to be positive, so we do the top minus the bottom function. But this integral right there represents the value of this area, right? We could also write it as, we could actually plug in the x squared plus 2 and the x squared minus 2x. If we were to do that, we would get something that looks like this. X squared plus 2 minus x squared minus 2x dx. That would give us the integral from 0 to 2 of 2x plus 2, which is obviously super solvable, right? But they don't ask us for that. So really, this first integral that we write that takes us like 3 seconds is completely acceptable because they ask us to write but not evaluate. So we are done with part A. Pretty simple, kind of feels like a free 2 points, right? Not a lot of actual calculus going on, and we'll take that, right? It's a really nice thing for us. But now, part B. Part B is looking like it's going to be a difficult one because it actually asks us to show our work. Sucks, right? Having to actually do the calculus. But part B says, let S be the region bounded by the graph of G and the x-axis from 2 to 5. So we're looking at the interval from 2 to 5. And it says region S is the base of a solid. For this solid, at each x, the cross-section perpendicular to the x-axis is a rectangle with height equal to half its base in region S. And it asks us to find the volume of the solid. and show the work that leads to your answer. Okay, so this is a little bit challenging. I'm going to slightly recreate this graph. So we have our x-axis, right? We have our parabola that kind of goes up like this. Then we have our bound at x is equal to 5. This point right here is at x is equal to 2. And that region is S, right? This is our region S. Now, for these cross-sectional volume questions, right, what we're essentially saying is this is the base, and then it's reaching up, and I don't know if you can really tell this, but we're going up out of the page to create this solid at each of the points. And it says the cross-sections are perpendicular to the x-axis. So we're kind of having these vertical cross-sections, right? And it says at each x, the cross-section perpendicular to the x-axis is a rectangle with height equal to half of its base in region S. So we have a rectangle, right? And these are the cross-sections. Our base is going to be represented by the value of this function, or the height of this function. So in this case, its height is going to be the value of g of x, because it's just how high this cross-section is. And this function is g of x. And our height is going to be half of that, or g of x divided by 2. And for cross-sections, what we do is we integrate over our interval from 2 to 5 of the area of these cross-sections. And the area of my cross-section is going to be base times height, or g of x squared divided by 2 dx, because that is the area of this rectangle in terms of the cross-section, right? Now, this would be awesome if it was another write but do not evaluate, but they do ask us to evaluate this one, so we have to work out the answer. And thankfully, this is going to be worth a lot of points, so it'll be worthwhile in the end. But let's expand out this g of x squared. We know that, I'll put it up here, but g of x, it is equal to x squared minus 2x. I'm going to pull the 1/2 to the outside. So this will be 1/2 times the integral from 2 to 5 of x squared minus 2x squared dx. Now we're going to FOIL it out, right? We would get 1/2, still integral from 2 to 5, but now it is x to the 4th minus 4x cubed plus 4x squared dx. So you can probably tell by now, but this is going to get a little bit ugly. So let's keep going though. So this will equal 1/2 times the integral, or actually we're going to go ahead and integrate it. So 1/2 times, let's integrate this polynomial. Give us x to the 5th over 5 minus x to the 4th plus 4/3 x cubed. And that's just doing, some classic power rule on this. We're going from 2 to 5. So now, I wish that there was a way to, make this simpler. I cannot find it, realistically. So we got to plug in some values, right? When we plug these in, this will be, I'll keep the 1/2 on the outside. We'll kind of think about that at the end. When I plug in 5, we get 5 to the 5th power over 5 minus 5 to the 4th power plus 4/3 times 5 cubed minus, when I plug in 2, I'll go ahead and evaluate this. 2 to the 5th power is 32. So minus 32 over 5 minus 2 to the 4th, which is 16, plus 4/3 times 2 cubed, which is 4/3 times 8, 32 over 3. Now, the one nice thing about this problem is this 5 to the 5th over 5 minus 5 to the 4th power. When I divide by 5, it's like reducing my exponent by 1. So this gives me 5 to the 4th minus 5 to the 4th. So those cancel out, which is like the only pretty thing about this question. So now, still evaluating, I get 4 over 3 times 5 cubed, which is 125. So 500 over 3 minus 32 over 5 plus 16 minus 32 over 3. And this will give us 1/2 times, when I do 500 over 3 minus 32 over 3, I get 468 over 3, which, to conserve some time, you can divide it out, and you would get 156 plus 16 minus 32 over 5. I don't know why I wrote that so janky. But this will equal 1/2 times 172 minus 32 over 5. If I finally distribute this 1/2, it'll give me 86 minus 16 over 5, which gives us a final value of 414 divided by 5. And that is my final answer. As insane as that is, there's a reason that this work is worth 4 points, right? This is actually an insane question, right? But that is our final answer. So, hopefully that makes sense. The cross sections at the beginning, actually constructing this shape, challenging, right? 100%. But just getting this integral right here already gives us a point. Correctly, it gives us 2 points. If we both get it in terms of g of x and do the actual function in terms of x, that's 2 points off the rip. So maybe if you get to this point and you're like, I hate algebra, I can't do this, for the sake of time, it's completely reasonable to stop kind of at this point. You can't do the algebra out, you're running out of time, you're on the last question, right? It is completely logical to potentially move on for the sake of finding easier questions. So completely reasonable there. But now we are going to move on to part C. And as we move to part C, I ran out of paper. So I need to actually open one real quick. See if I can do this effectively. This was kind of stupid of me. I thought I had enough paper left, but I did not. But now we can move on for the final part of this question and the final part of this entire year of FRQs. So here we go, part C. And we see our favorite words we could ever see: write but do not evaluate. No real math, no algebra, thank goodness. But it says write but do not evaluate an integral expression that gives the volume of the solid generated when the region S, as described in part B, is rotated about the horizontal line y is equal to 20. So for this, right, we have a region that we're trying to rotate around a curve. And I'll try and do my best to draw it again. So we have the x-axis, now we have this curve, and we have this dashed line. We have this region S, and we're trying to rotate it around this line, y is equal to 20, right? So as we try and revolve it around y is equal to 20, we're going to have an outer radius and an inner radius. And when we're integrating, right, trying to find the volume of one of these revolved figures, we're going to be using Washer method, right? Now for Washer method, we have a really, really simple formula that we learned, works every single time without fail. It is pi times the integral over our bounds in terms of x, right? Which in this case are from 2 to 5. And it is our outer radius which in this case is 20, right? Because we're going from 0 to 20. But it's our outer radius minus the value of the function, which in this case is just 0, right? Minus my distance, 20 once again, minus the value of my inner radius, right? Which in this case is equal to this function, g of x, which, I'll just write as g of x for now. We get this dx. Sorry, it's getting cramped. But I could rewrite this integral a little bit easier. Pi times the integral from 2 to 5 of 20 squared minus 20 minus g of x squared dx. And that will be an integral that represents the volume of this revolved figure. Now, we could also put this in terms of x rather than writing g of x. So we could say it is pi times the integral from 2 to 5, 20 squared minus 20, and it's going to be minus x squared plus 2x squared dx. So quite a mess. We're glad that we don't have to evaluate that because it would be super ugly, right? But this integral would represent the volume of that rotated figure, right? So hopefully that was helpful. We got through question number 6, finished the 2024 FRQ. Super excited about that. And I hope to see you guys again soon. Yeah, happy practicing. Have a good one.